let's say we're looking at the relative abundances of uranium-235 and 238. So the half-life of each of these, if you look them up, for uranium-235 is about 7.1 times 10 to the 8th years. And then the half-life for uranium-235, 238, no, 235, is about 4.5 billion years. So we'll just write 4.5. Or better yet, let's write this as 710 million years. So I can fit everything in there. So we want to know what were the relative abundances of each of these at a time of 4.54 billion years when the Earth was formed. So the number of half-lives that each of that would have elapsed during this time for each of these, which we can compute, it's just going to be this time divided by the half-life, right? So this would be about 6.39 half-lives for uranium-235. And then for uranium-238, it's basically just like one half-life. All right, if we do 4.54 divided by 4.5, we can write it as like 1.009 half-lives. And so assuming that the current abundance is that like 0.7% of all uranium is 235 at the moment. And then the other like 99.3% is uranium-238, given those present day abundances. What we can do then is we'll write like the mass of 235 over the mass of 238. And we know like the mass as a function of time is just going to be like some initial mass times e to the minus lambda t, where lambda is like the natural log of 2 over the half-life, right? So another way of writing it is like the initial mass times 1/2 times t over the half-life. And so at the present day, if this currently equals like 0.007 over 0.993, right? Which if we plug that number in, this is about 7.05 times 10 to the negative third. That's the current day abundance. Let me move this down here. Then the initial abundances, the current day abundance, we'll say like m naught 235 over m naught 238 should be equal to this number, 7.05 times 10 to the negative third, times 1/2 to the power, how much time has elapsed, negative t, or let me just take one more step and write this so that it's as clear as can be. So this is 1/2 times t over the half-life of uranium-235 divided by 1/2 times t to the t over the half-life of uranium-238, something like that. So if we multiply both sides by this, what we'll get is like the ratio of our initial mass of 235 to our original mass of 238 is going to be basically like 1/2. We can combine the exponents. So it'll be t times 1 over the half-life of uranium-238, which I'm trying to think. Maybe I'll just put a T238 for that, over minus 1 over T235. And then that's times 7.05 times 10 to the negative third. So if we do that, we'll get the ratio of these two we'll get 1.69 times 10 to the negative fourth. So that's like our relative abundances of these two. Actually, sorry, we don't really even need this number right here. So this should give us about 0.298 or something like 2989. So basically 0.299. And so that translates to about 76.93% uranium-238, and then the remaining like 23.07% would have been 235.